Okay, hello everyone, welcome. Today we are restarting our ECR seminars for this semester. We are very lucky to start with Wuhyun Sohn, one of our own postdocs from the cosmology group here in CASI. So I'm sure most of you know him personally already, but for those of you that haven't had the pleasure, so Wuhyun won the Korea Presidential Science Scholarship when he finished his high school, and that meant that he could attend Cambridge for pretty much all of his education from his bachelor from to his PhD. After his PhD, he came here to CASI, and he's been working here for the last couple of years. He is quite an expert on CMB cosmology. A lot of his works revolve about reconstruction, primordial non-gang societies, and so on. And today he is going to introduce some of his work for us. So without further ado, please go ahead.
Right. Thank you for the introduction, and thank you for having me in this ECR seminar series. Today I'll be talking about some of our recent research works under the title CMB Studies of Primordial Features and Non-Universe Physics. And so this is the roadmap of the talk that I'm going to give today. So first, I'll start with some introductions on the inflation and CMB. And in particular, I'll talk about how the 2-point and the 3-point functions of the CMB can be used to study the early universe. And in the second part, I'll in particular focus on primordial features that is predicted by many inflation models, and introduce 2 of our recent works on free-form reconstruction and analytical search with genetic algorithms. And in the third part of the talk, I'll focus on primordial non-Gaussianity and how we can constrain the early universe using CMB bispectrum via primordial non-Gaussianity. In particular, I'm going to talk about our latest code that is being public called CMB Best, which is a high resolution bispectrum estimator that has been thoroughly tested. I'll show some demos and show some applications. For example, universe inflation. Right, so without further ado, starting with the introduction, all cosmology talks have to start with this plot. So cosmic inflation is the leading paradigm of the early universe, which involves a period of exponential expansion in the early universe in the fraction of a second after the Big Bang. And this has been very widely accepted because it solves many problems such as horizon flatness and monopole problems of the Big Bang cosmology. And to have inflation means to have something that drives inflation, and the simplest candidate for that is a single scalar field which is solely rolling down the potential field phi. And if we have this solely rolling down, slow roll, then the scalar field has negative pressure, which then drives exponential expansion of the background. And as long as the slow roll parameters defined as follows is less than 1, we can have a 50 to 60 e-folds long inflation exponential expansion that is required to solve the horizon problem. Not only that, under this kind of scalar field inflation model, we have the small scale quantum fluctuations of the inflaton that, due to the rapid expansion of the universe, gets stretched out and then freezes. And such quantum fluctuations that eventually freezes, they seed the curvature perturbations of the universe we observe, which then sets the initial conditions of the structure of the universe that we observe today. So the inflationary epoch is followed by radiation domination, matter domination, during which the CMB photons, cosmic microwave background photons, decouple. And because these inflations as the primordial initial conditions, these perturbations are also imprinted on the CMB photons distribution functions. And because CMB decouples only when the universe is about 300,000 years old, the perturbations remain very small. So 10 to the minus 5 order of magnitude. And thanks to this, the CMB perturbations are roughly linear in terms of the primordial fluctuations, which makes it an ideal probe for studying the universe physics. And CMB therefore provides a unique window to see the very early universe and it was not shift to 1100. Right, so when we observe the CMB anisotropes, what we observe is the small differences in the CMB temperature and the EMB fluid polarizations. And it's useful to decompose this in harmonic space as follows. And because the CMB anisotropes appear pretty much Gaussian distributed, a lot of its statistical information is captured in the covariance, which is given by this called power spectrum, CLs. And these CLs has been measured to great accuracy in the Planck satellite experiment, and as you can see in the plot on the left. And lambda CDM, the standard model of cosmology, it successfully explains this data set with only 6 degrees of freedom, 4 of which contains the composition and evolution of the universe, and 2 containing the initial conditions that we just discussed. So the initial conditions are parameterized by these 2 parameters, AS and NS, and assuming this power law, primordial power spectrum given on the bottom right. So I want to emphasize that it is really remarkable how only 6 degrees of freedom are required to fit so many degrees of freedom present in the data. So despite these achievements, we were not free from assumptions coming on the way to that plot. In particular, in the inflationary part, we have assumed quite a few things, including it's a single field inflation with slow conditions, and some other assumptions about the action and the vacuum state. But in fact, there are so many other inflation models that are physically well motivated that breaks one or more of these assumptions. So, for example, we can have a multi-field inflation and deviation from this slow due to many different reasons, and so on. In fact, there's a whole encyclopedia paper on the different viable inflation models that are still viable, is still not constrained. And in particular, I would like to focus our attention on some of the some inflationary scenarios where there are features or oscillations that are created in the primordial power spectrum. And this can be due to multiple reasons. First, there can be features in the inflation potential, which should introduce some oscillations over in the end to the primordial power spectrum, as you can see here, these oscillations. Or in some in the multi-field models, if there are sharp turns in the trajectory, there will be some transient deviations, oscillations on the power spectrum. And motivated by these, I'll go to the second part and discuss the primordial features. And we're going to use the CMB power spectrum to discuss this. So this is our recent work on freeform construction of the primordial power spectrum using CMB. I've chosen the best photo from myself. And so the problem we went to study is as follows. So the observed CMB power spectrum is related linearly to the primordial power spectrum, almost linearly under this this formula. And as we just said, like lambda CDM parameterizes these parts using 6 parameters. The 2 A's and NS parameters say that the primordial power spectrum follows the power law. And our goal is to relax this condition and instead introduce a lot more degrees of freedom. So our goal is to, given data and transfer functions, we like to reconstruct the free-form primordial power spectrum by allowing many degrees of freedom. And this can serve as a catch-all spectra, which may contain all possible hints of features that might be in the primordial feature and supported by the data. This kind of methods have been studied in the literature by many different collaborators, but here we are going to focus on something that is inspired by image analysis. So there's a very similar problem in image analysis where the observed image is a blurred version of the underlying image due to this spread functions. And you can see this image, this is like this. And popular techniques to recover these the true image is to use Richardson-Lucy deconvolution, which is an iterative reconstruction technique, which iteratively gets from the data to underlying image. And this method has been adapted to cosmological contexts by Nicholas Arman and his collaborators. And this includes some weights based on this error information, as you can see on the right-hand side. So I've prepared some CAD images to test these techniques, where this CAD image is blurred and added some extra noise. And as you can see in this, you can see that as the MRL iterations passes, we get an image that is sharper and sharper and closer to the original image. But at the same time, you'll also notice that there's noise amplification, which creates some artifacts, these grainy artifacts in the image, which motivated us to study the regularization techniques that get rid of these artifacts. And that's one of the novelty of our work, which we introduced the regularized MRL reconstruction, which incorporates this diffusive term in their iterations. This diffusion equation makes it so that at every iterations, each pixel values will smooth out and diffuse to nearby pixels, unless it's strongly favored by the data, in which the original MRL part of overcomes it and keeps that feature. So using this method, we have indeed reduced the noise fitting. By comparing the least square error to the true underlying image, we find that this indeed is better. So by comparing the one with and without the regularization, you can see that a lot fewer noise artifacts, weaker noise artifacts. And while we are on using different image analysis techniques to add to this reconstruction, we also studied this total variation regularization method, which is often used in image denoising. And this can also be incorporated in our iterations, iteratively through this, which acts to minimize the sum of total gradients in the image. And this is known to have some characteristic patchy style, where there are lots of regions, lots of pixels with very similar values of the pixel values separated by some sharp edges. So using these two new regularization techniques, we applied this modified Richardson-Lucy deconvolution algorithm to primordial path spectrum, actually coming back to CMB data. We have used the ChemSpec CLs, which is a reanalysis of 2018 results. We use all TTT and ED data, and here are some reconstructed primordial path spectra from different methods. When we look at these reconstructions and study the goodness of fit as the number of iterations goes on, we see that as iterations goes on, we do improve the fit to the data and have less total chi-squared. When we look at the breakdown and see the TT, T, and E parts of these goodness of fit, we find that while the TT path spectra keeps improving, the polarization part doesn't necessarily continue improving, and in fact, it gets worse as the iteration goes on. And this is because the method is trying to overfit the noise in the TT data, so at the cost of sacrificing some goodness of fit to the other two. And in fact, to obtain some form of primordial path spectra that is better than the power law in each of these respective channels, we find that introducing the regularization, either the diffusive one or total variation regularization, is necessary to achieve this. Furthermore, we also test the statistical significance of these reconstructed results by studying some mock CLs, generating using the full covariance matrix to obtain the blue regions, 1 sigma and 2 sigma regions shown in this plot. And as you can see from the residual here, we don't quite yet have some statistically significant deviations from the power law spectrum. Right. So for more details, please refer to the paper on the archive. And next, I'll introduce our more recent work read by Kushal. Unfortunately not in this room, but yeah, it's titled "Searching for Local Features in Primordial Power Spectrum using Genetic Algorithms." So we have the same problem in hand where the CMB CLs are coming from the CMB transfer functions and primordial power spectra of interest. But instead of relaxing these AS and NS to include many degrees of freedom, we would like to focus on some extensions that are only as a few handful of new extra parameters. And we would like to find the analytical form for PK. But we would like to introduce as many types of analytical forms that are motivated by the theory. So for example, we could look at this log space oscillations, or like this a log K kind of type, or the same with some envelopes. Some envelopes that looks like this. So this will have some extra parameters, as you can see, like omega, phi, sigma, and so on. And this would be great for searching for viable features that is motivated by many theories. But the main challenge is that there are such big functional and parameter space that we need to explore to achieve this. And this is where genetic algorithms come in. And these are some biology-inspired algorithm optimization problems, which has been used in many different contexts, such as making some robots walk in a straight line. And in this algorithm, each individual has some genes that determine one's fitness. For example, in some generation, there are multiple individuals with different genes. After evaluating some fitness functions, we would remove those that are not as fit and only keep the top few that have good fitness function values. And then there's a stochastic step where there are many crossovers and mutations among those populations that survived, and crossover to keep those genes that are good for the fitness, and mutation to introduce some new genes that helps explore the space of genes and space of time that we would like to optimize. And coming back to the cosmology context, for genes correspond to analytical form of the primordial power spectrum, and the fitness here will be the CMB, actual punk CMB like language. And for genes, we have different functional forms. In particular, we use this kind of functional form, where GBI are some different functional forms that are oscillatory, or it's a combination of polynomial and oscillatory functions, and is parameterized by these parameters A, B, C, and D. And by studying these, applying genetic algorithm on this, this GA provides a set of analytical power spectrum that fit the CMB data well. So first, we tried some mock data, applied to some mock data that is generated from CL's data that actually comes from some oscillatory decay. As you can see here, the dashed black line is the true underlying one under this mock. And as you can see from the best fit, the best population in some generation, in the genetic algorithm, it is able to retrieve the main features in an analytical way. And moving to the actual likelihood, we have seen that by applying to the Planck 2018 likelihood, first on the left, as the generations of this genetic algorithm goes on, the thinness on the left, the y-axis is the chi-squared error, so it measures the goodness of fit. As the generation increases, there are more and more individuals that have improved chi-squared fit to the data. And by looking at these individual populations on the right, we do indeed have some forms of primordial power spectrum that is oscillatory and also localized in some K range that improves the fit to the data significantly. However, we would like to emphasize that this method isn't for providing some model, some oscillatory primordial power spectrum that is necessarily better than the power law. We have increased the complexity, has surged on the intensive large parameter space. The aim of these GA constructions, these primordial power spectrum we found, is to give hints to where potential oscillations in the primordial power spectrum might lie. So for more details, please refer to the paper shown above. And now I'll move to the third part of the talk, which will be about constraining the universe using the CMB spectrum using triangle sensitivity. So I mentioned earlier that the primordial perturbations come from the quantum fluctuations of the infotron, and we know from CMB that these primordial perturbations appear approximately Gaussian distributed. So if you look at the probability distribution, it looks like this Gaussian distribution. However, there are many other models of inflation that can predict some deviations from this Gaussianity. For example, the famous local norm Gaussianity as an extra term that is proportional to the square of the Gaussian field. And if you introduce such terms, as you can see on the left, you see deviations from the Gaussian distributions. And in such cases, just looking at the 1 and 2 point functions are not sufficient. As you can tell by plugging in this formula to the mean and variance, we see that the mean and variance are the same as the Gaussian field, even though the probability distribution is different, which motivates us to study higher order statistics. For example, if we set the 3-point function skewness in this example, we find that this indeed depends on this parameter NL and is different from the Gaussian parameter. So by the most natural thing to study next is then the higher order correlation functions of the primordial power spectrum. The primordial curvature perturbations, which is theta, and such 3-point functions for the bispectrum. And primordial Gaussianity PNG can create such non-zero bispectrum, which is parameterized by this amplitude FNL and the shape. And these amplitude and shape is different for different types of models of inflation of the study. And in particular, these shapes are very distinct and is defined on a 3D. It's a 3-dimensional function that is defined in this domain, constrained by triangle. And these 3-point functions is linearly related to the CMB bispectrum, which is a 3-point function in the CMB and isotropies through this relation. And by studying the 3-point function and CMB, we can get information about this primordial bispectrum. However, the main downside is that, as you can see from the many terms appearing in this integral, it is computationally very expensive, and we are somewhat restricted on how thoroughly we can study this. The actual estimation process to constrain the amplitude of this primordial Gaussianity is pretty simple. Once we have some observed CMB bispectrum, We then come up with different templates that is inspired by different classes of models, such as multi-field models, or like some DBI inflation, some non-canonical kinetic time models, and do a linear fit to estimate FNR. In fact, part of 2018 analysis has given like the most stringent constraints on these parameters, which are so far all consistent with 0. And those are not only fixed. In Planck team has constrained many different templates, and if you include the different parameters that is involved in those templates, there are more than 1,000 uncorrelated models. As you can see, like each of these points are different models on the study, which is only a subset of that has been seen. But even though we have such thorough model space, we haven't found any significant evidence for primary sampling yet. So far everything is consistent with single field slow inflation, and we might want to just give up and stop studying exciting models. But that's where our recent work on CMB bispectrum come in. So collaboration with my PhD supervisor, and we have developed a new bispectrum estimation pipeline called CMB Best, short for CMB bispectrum estimator, which can work with better data that is coming soon from observatory and stage 4 and so on, and serves as a new and independent complementary pipeline for the analysis for these data. And we'll also be able to study using this high resolution basis, can study previously unconstrained models that was barred by computational challenges. So the core idea behind this this new pipeline is as follows. FNL estimation is in broadly speaking, a two-step process. When we start with some primary bispectrum template of interest, we project it using the CMB transfer functions to some late-time bispectrum, how we expect to see in the CMB sky today. And by fitting these to the actual data, we have estimation for FNL. So what our code does is that by expanding the first part, this primordial bispectrum part, in terms of separable basis, given like this QA, QB, QC, by pre-computing a lot of results, we massively reduce the amount of computations that's necessary, and immediately use this expansion coefficients to get constraints in FNL. So there are some technical points, distinctions about it and conventional methods, but for those, please refer to our paper. And the main challenge in this pipeline was the computational part. So we had to thoroughly optimize this in many different levels in terms of the high performance computing, and also in more like a methodological level. In particular, we developed this new numerical quadrature method for integrals over this specific tetrabit domains. These tetrabit domains are pretty weirdly shaped, and a three-dimensional integral using the conventional simple, straightforward methods are very inefficient and not necessarily very accurate. It doesn't scale very well with the number of grid evaluations required. So using our new methods, we used tetrapod. We have numerically came up with some quadrature scheme, numerical integration scheme that is much more efficient, only requires much fewer points, but still contains a good integration precision. Public code can be found in this repository. Using those optimizations, we have completed the code, and we have validated it pretty thoroughly using the conventional data. So with comparing with the modal estimator from 2018, and also using the Planck's official mock simulations, Gaussian simulations, we have validated map by map that our method is indeed consistent with previous results. And also to show what was promised, this high-resolution estimator can study highly obstruction models that hasn't been studied before. We studied this templates, bispectrum templates that has some envelope function multiplied by high-frequency oscillation. And by studying some targeted oscillatory functions with fixed omega, by expanding just the envelope part and multiplying by some oscillatory mode functions, we have been able to study some complex shapes with high oscillations, which previously couldn't be done due to computational challenges. And through this, we got new FNL constraints using existing CMB data. And the results are follows. And even though, of course, we still don't find a significant value of FNL, in principle, we could apply these methods to any particular frequency of interest in the future experiments. Our code is now public, and you can find the public code in this GitHub repository. And in particular, this is our first code to our knowledge, which anyone can just plug in their favorite bispectrum template and get Planck 2018 constraints in a matter of seconds. And here I prepared some simple demo on how to use the code once you have everything set up and installed. You just have to load in Python, Jupyter library, notebook or something. Just load the Python library and create basis object, as you can see in the first line, which specifies the type of basis or whether if you include polarization data or not. And then you create models that we provide some preset templates such as local, logical, and orthogonal. So using this basis object and list of models, you can immediately get constraints by single function constraint models. And we also provide some utility functions to print and summarize and plot these results given as this constraint object. A slightly more complicated, more advanced demonstration would be to study arbitrary bispectrum shapes, not just the ones that we provide. In this case, what you do is you create a custom model. So you define some my function, which is a shape that you like to constrain, which is not in the preset shapes. And by creating a custom model with this shape function included as a Python object, you can then constrain these models using the same methods that I've shown before to get FNL constraints from this. So here there are some things about the conventions of the normalization and accuracy of the basis expansion you need to be careful about. But for those, I refer you to read the paper. So these we have been since this code is ready, we have been trying to apply to many different models of interest, especially the ones integrated by different theories. In particular, we have been working on getting some constraints on this D-host inflation in collaboration with people. So this is still preliminary, but it's soon to be on hopefully next month. So D-host theory, short for degenerate higher order scalar tensor theories, is a generalization of the general relativity, in which it is the most general scalar tensor theory with one propagating scalar degree of freedom, and it doesn't have any ghosts from here. And this is achieved by setting some degeneracy conditions to avoid its instabilities and ghosts. And while this is used to explain, many people use this to explain the late time oscillatory expansion. Instead of having a cosmological constant dark energy, the same idea can be used to apply to early time oscillatory expansion to explain inflation. And the action, the most general D-host action, can be written in terms of this form. And here, by itself, D-host action does not provide primordial power spectrum that is consistent with the observations, because it is completely scale invariant. So to have this NS value not equal to 1, as we know from CMB observations, we need some small interaction terms with some potential field fact, which has been introduced to provide some inflation model that is consistent at the power spectrum level in this work by Brooks and Masame. And now we study the bispectrum predictions from this inflation model, where we have 5 free parameters that remain after fixing the other degrees of freedom using the power spectrum. And I'll spare some technical details, but if you look at the bispectrum shapes that is introduced by each of these parameters, these are all blue lines. Even though the 5 parameters are different, after some rescaling, these all show very similar shape dependence on the bispectrum. So there's effectively one parameter that we need to vary to study the CMB bispectrum constraints. And here are our constraints. We are in this triangle plot, we are showing this F base. This is a contribution that exists to the diffuse bispectrum that doesn't depend on any extra parameters. So in our theory, this is fixed to 1. So our theory will correspond to this line at base equals 1. And as you can see from these contours, that comes from the Planck temperature and temperature plus polarization constraints. The likelihood ratio is -19, so it's very small. And despite having so much degrees of freedom and being able to explain the primordial power spectrum constraints very well, when we look at the simplified spectrum constraints, we actually find that the model is strongly disfavored, even though there are 5 different parameters. So yeah, there was quick applications. Yeah, please stay tuned for the paper that's still coming soon. To summarize the talk, I'll give you just 3 quick messages. First, as you know, the current observations are all consistent with the simplest inflation model and the CDM. But in theory, there are so many more interesting inflation models that predict deviations from those. And we have developed some robust tools to study these more interesting inflation models, in particular to study primordial features and primordial Gaussianity using the CMB power spectrum and bispectrum. And because of this, we ask you to stay tuned for coming surveys where we are going to apply these new tools to see if there's any more interesting things going on in the inflation. And thank you for your attention. Happy to take questions.
Okay, thank you very much for this amazing talk. Please, everyone that is listening online, if you have any questions, please raise your hand on Zoom.
No one.
Oh, everyone's.